let's talk about the Lenz law. Lenz law states that the direction of induced current, like if I'm taking the right hand thumb rule in this way, like this is the curl of my fingers and here I have the thumb direction, okay? So this is the normal direction of current, let's suppose, but when I'm talking about the induced current, it is just opposite of that, okay? So induced current is always opposite of the normal current direction which I'm getting from right hand thumb rule. Now in a circuit is such that it opposes the cause or the change which produces it, like due to whichever force it's being produced, it's always opposite to that. So we can just remember this with a kind of a trick, like we are not agreeing to the talks which our mother is saying. So the mother who produced us, we are not agreeing to the direction what she is giving us. It's like that, okay? Now we have to show that Lenz law is a consequence of the law of conservation of energy. First of all, you have to write an answer that whether a magnet is moved towards or away from the closed coil. Like if I'm taking this as the closed coil for an example, if I'm bringing the magnet towards or away from this, then the induced current is always opposing the motion of the magnet only by the prediction of Lenz law. So that's why I used to say that Lenz law is always a consequence of the law of conservation of energy. Next we have a kind of thing, like first of all we will be talking about what is motional EMF and then how to determine its direction, okay? Now what is motional EMF? A kind of EMF which is induced across the ends of the conductor. Let's suppose this is my conductor and across its ends, if it is being induced due to the motion in a magnetic field. Whenever there is a change in the magnetic field, there is a motion in that. Due to that, whatever EMF is induced is called as the motional EMF. The name itself is suggesting that. And we have EMF, which is E is equal to BLV formula, and we can write this V velocity as dx by dt. So that's why we are saying that BLV can also be written as minus BL dx by dt, and why this negative sign is coming we already understood in the previous lecture. Now how to determine the direction? So the direction of the induced current can be determined by using Fleming's right hand rule. Whenever the word induced is coming into the picture, we will be using Fleming's right hand rule. Else for the normal directions, like for normal prediction of current or the velocity or the force, we will be using Fleming's left hand rule as usual, which we already studied in the previous lectures. But whenever we have to calculate for the induced words, it's always right hand rule. Clear? Now we have the derivation. What I'm taking a length L, or let's suppose X of the loop, which is lying inside the magnetic field. So I'm taking the magnetic field consideration here and I'm taking the conductor length as, let's suppose, X. Okay. So magnetic flux formula, we already know it is magnetic field into area. So area can also be written as L into X. Like it is length into breadth. So L into X. See. This is basically length, this one, and this is X kind of thing, which we are taking from here. So flux formula we got BLX. Now according to Faraday's second law, we already studied that magnitude of the induced EMF is always equal to the rate of change of flux. Rate matlab it is divided by time. Okay. So or we can also pronounce that induced EMF is equal to rate of change of magnetic flux or change of magnetic flux with respect to time. Now this flux value we can put on from this first equation here, and we know magnetic field and the length of the conductor is constant. Only the width is changing because as soon as the conductor will be moving here or there, then the value of the X will be changing. So we wrote it dx by dt in the derivative term, and we know that this is minus V and we get E is equal to BLV. So this is the final formula that we are getting from this, okay, motional EMF. Done. And we know this dx by dt is equal to minus V because as soon as we are increasing, we are going ahead in the direction of X, the velocity is decreasing kind of thing. So it's doing the reverse thing. So that's why we are mentioning that velocity is in the decreasing direction. Now this induced EMF BLV is called as motional EMF, which we are talking about in the derivation earlier. So why this is called as motional EMF? Because this EMF is induced due to the motion of the conductor in a magnetic field. That's why. Because as soon as we are bringing the motion inside a conductor, due to that the magnetic field is getting induced. Okay. Next. Now what is Fleming's right hand rule? It's exactly same what is Fleming's left hand rule. Just what you have to remember, if this is my thumb, this is my first finger and this is my middle finger, then father means force, mother means magnetic field and child means current. Just the difference is that it will be giving us the induced force, induced magnetic field and induced current. Clear? So this is what written here. And you have to remember that whenever we are talking about the induced word, then only we are using Fleming's right hand rule. Else Fleming's left hand rule is being used for the normal things. Now we have the next thing, which is motional EMF from the Lorentz force and the energy conservation. So we have the accumulation of the charges at the two ends continues till these forces balance each other. Which means we have to equate this electric and the magnetic force. Okay. And from magnetic force we already studied, it is QVB, and electric field, electric force is Q into E. So we can just neglect or cut out the values of Q and we are getting V into B is equal to E. Also we know that the potential difference between the ends, let's suppose I am taking P and Q, two ends, then potential difference value is always E into L, and electric field value from here, from the first equation, we can substitute this back to here, which is VBL. So also we are again getting the same formula of induced EMF, that is BVL again, second time. Now we can just divide this value of induced EMF, which we used to, let's suppose, just like the potential difference only, divided by R. So by Ohm's law, I is equal to V by R. So we can directly get the value of induced current. Third thing is force on the movable arm. If the arm is moving, and in the earlier derivation, we just now saw that the magnetic field is inside the plane of the paper, that is going into the plane of paper. And we have the second thing that is being written here, which is, see, magnetic field and the force. So it is lying always perpendicular to that. That's why we are taking it as sine 90 and we are placing the formula of force as ILB. The value of I we can substitute back from here. L and B will remain as it is. So we are getting the formula of the force, which is B square L square V by R. Power formula, we know that we can multiply the force with velocity and we are just getting the same term multiplied by the one more velocity term. Clear? Next we have the power dissipated as Joule's law, which is directly by I square R only, and we are again getting the same formula for the power. So these are the two methods we can calculate the value of the power, and the expression is always same. Clear? Next we have the energy consideration. See, the mechanical energy which is expended to maintain the motion on the movable arm, whatever the arm is being moving from here to here like that, First of all, that mechanical energy is converted into electrical energy, which is inducing the EMF into that, right? And then it is converted into thermal energy. And this is consistent with the law of conservation of energy. So here we are dictating that how the energy consideration is being taken into the picture, okay? Next we have the relation between induced charge and the change in magnetic flux. Change in magnetic flux formula we already derived from the Faraday's law, that change in EMF is equal to change in flux by time, right? And if we know R is the total resistance of the closed loop, then the induced current can be written as I is equal to V by R, or in this case the V is EMF, right? So we can write this current value again as Q by T, we already learned in class 10th, and equate it to E by R, right? EMF by R. And this EMF value I can substitute from here as delta phi by delta T, and R will remain as it is in the denominator. So what we are taking, that this and this will get cancelled and the change in Q is equal to change in flux by R. So this is the relation that we wanted to derive between induced charge and change in magnetic flux. Induced charge and change in magnetic flux. So we are getting a note that the induced charge depends on the net flux and not on the time value. Okay. So thus the induced charge does not depend on the rate of the change of magnetic flux. It only and only depend upon the change in magnetic flux, not in the rate. Rate means it is not depending upon the time, right? Yeah. Now we have certain methods of generating the induced EMF that we'll do in next lecture.